Great. Let's now go back to a theorem that we saw earlier, the closure under union. We proved earlier that if A and B are regular languages, then also the union of A and B is a regular language. What was the proof idea? Was to enlarge the set of states to the Cartesian product, so that the first coordinate tracks states in A and the second tracks states in B. Okay? And that worked, but using NFAs, we can give a much simpler proof. Okay? So if you give me a DFA MA whose language is A and a DFA MB whose language is B, I'm going to construct an NFA N whose language is A union B as follows. So here is my DFA for A, my DFA for B. My DFA N will have a new star state and will have two epsilon transitions from it, one to the star state of MA and one to the star state of MB. And that's it, right? You accept if you can if you can have a sequence of states. So at the beginning you can follow one of these two epsilon transitions and then you go into a corresponding DFA. So here is the formal construction. So you're given these two DFAs and you want to construct the NFA. So how do we construct it? What's Q? What are we doing? Well, we're just adding one state, right? So you get the states from MA, the states from QB, and we add a state Q. The set of accept states is the union of accept states. And the transition function is what? Delta Rx from some state R. Well, if R is inside QA, then you should be doing like MA. So I'm just going to do delta A Rx. Okay. And if R is in QB, then what do you do? Well, you would just be doing a delta B Rx. Okay, the transition function of the DFA for B. And the new thing is what happens when you do an epsilon transition from Q, right? And here you go to, try this, will be to the set QA QB. Okay. The union of the star states of the DFAs. The language of N is now the A union B. Let's see an example. Let's consider the language of strings W, where the length of W, this denotes length, is divisible by 3, or W starts with a 1. Is this regular? Well, or is like union. So we are trying to write L as L1 union L2, where L1 and L2 are regular. And then we can apply the closure under union. So here is L1 and here is L2. Divisible by 3 in length is this. It's just a loop of length 3. And starting with a 1 is this DFA here. Okay. So we can use now the closure and the union to get a DFA for L, which is just the DFA for L1 and the DFA for L2, and then I add this new state with the epsilon transitions. So L is regular. Okay, let's now return to the question of closure under operation. So let's now look at the closure under concatenation. Okay, so if A and B are regular languages, then so is the concatenation A on B, which is the set of strings W, which can be written as X concatenation y for some x in A and some y in B. And the proof idea is the following. Here is my DFA for A. Here is my DFA for B. Okay, and I'm going to construct a new DFA n, new NFA n. Okay, which starts with the NFA for MA, and then from every accept state, I'm going to put epsilon transition to the start state of MB. Okay, and the accept states of MA will not be accept states anymore. Here is the formal construction. I'm given these two DFAs. I'm going to construct an NFA. What is Q? Is the union QA and QB. Okay, because I have both sets of states. What is Q? The start state in N will be just the start state of QA. What is the set of accept states? It is just FB, okay? Because the accept states of MA are not accept anymore. What about delta? Well, delta Rx, if R is in a QA, you're not treating an epsilon transition, it would be just like delta A Rx, the set containing delta A Rx. Okay, you just follow MA. If however you are in accept state of MA and you do an epsilon transition, then you will go to the start state of MB. Okay, and if you are in QB and you don't read an epsilon transition, then the transition just follows MB. So it's a set containing delta B Rx. The language of N is the concatenation of A and B. Here is an example. Consider the language W, where W contains a 1 after a 0. Is this regular? Here is an example of strings in L. So there is a 1 after a 0. So you can write L as the concatenation. So L0 is the set of strings which contain a 0, and then 1 is the set of strings which contains a 1. And now L becomes the concatenation of L0 and L1. Okay, here is the DFA for M0. It needs to contain at least 1 0. And here is a similar DFA for M1. It needs to contain at least 1 1. Okay, so if you concatenate, you get this NFA here, right? So the first thing is M0. This accept state is not accept anymore, but it has an epsilon transition to the start state of MB. And this implies that L is regular. Okay, what's left? Now A star, closure under the star cleaning. Okay, so if A is regular, then so is A star, which remember is the set of strings W that can be written as any number of concatenations of strings in A. Okay, and the proof idea is given a DFA MA whose language is A, I'm going to construct another NFA N whose language is A star as follows. I'm going to take my DFA, I'm going to box it, okay, and I'm going to put epsilon transitions from the accept states back to the start state. Okay, and there is a detail here that A star always contains the epsilon string, the empty string, okay, but the start state of M may not be accepted. So to correct that, I'm going to add a new state. I'm going to make it accept, and I'm going to have an epsilon transition to the start state of N. Here is the formal construction. Q is the same set of states as QA, union a new state Q. The accept states are the same as before, union the new state Q. And the transitions delta Rx, if R is in QA and X is not the empty symbol, would be just like the one in the DFA, MA. But if you do an epsilon transition from R, which is either the new start state or an accept state, okay, then you go where? Then you go to QA, the set containing QA, the start state of MA. The language of N is A star. Here's an example. Consider the language L of strings which have even length. Is this regular? So we can think of L as being the star of L0, where L0 is the language of strings with length 2. Okay, here is a DFA for M0. The language of M0 is the set L0 of strings of length 2. And you can use this construction, okay, to have now an NFA for L, which is L0 star. I'm going to add my epsilon transition back to the start state, and I'm going to have a new start state, which is accept, with an epsilon transition to the old start state. Okay. So all these languages are regular. Regular languages are closed under complementation, union, concatenation, and star.